Раз, раз. Раз, два, три.
Okay, so let's start our evening session. The first speaker is Oleg Kargaltsev of George Washington University, and he will be talking about X-ray, pulsar with nebulae, and not only X-ray. So Oleg, please go ahead.
Thank you, George, and thank you for invitation to the organizers, because I'm taking part in this conference for the third time, and it's always a great pleasure to be here. So I will be talking about the pulsar wind nebulae, and I will focus on reviewing recent developments in this area, and I will primarily restrict myself to the X-ray observations and a little bit, maybe I'll show a little bit of radio images. Simply because of the limited time, I will not be able to talk about the developments at very high energies, such as TeV and GeV. So there's been quite interesting developments there as well. I'm not going to be able to cover them. So a lot of new results and recent work that I will be showing is done in collaboration with these people, and this is really quite incomplete list here, right? So let me start a little bit with a historical introduction. So these are images of pulsar wind nebulae, which are really brightest pulsar wind nebulae, which were obtained with ROSAT, right? So maybe you still can recognize, if you saw just Chandra images, maybe you still can recognize which pulsar wind nebulae are these. So this is a Vela, Crab, and MSH 1552. I will, of course, show the Chandra images as well. So even with these sort of data, the basic properties can be actually evaluated, and the basic physics can be put in place. So there is this picture that's been out there for a while, and it hasn't changed a lot. I mean, the details have changed, and many physics has been added into this picture, but sort of at large, it still remains more or less valid. So I just took the picture from the Haranyan, but of course it's actually based on the earlier works, in particular the important work by Kennel and Karaniti. So what's shown here is there is a neutron star, right? So this magnetized sphere that produces particles and large amplitude electromagnetic wave, right? So this wind of particles is initially, we will call it like unshocked wind, right? It goes through the termination shock because it needs to slow down. Initially, it's highly relativistic flow with Lorentz factor of maybe few hundred. So it goes through this termination shock, after which there is another region which is actually the visible nebula. That's what we really refer to as a pulsar wind nebula, the synchrotron nebula over here, where the motion of particles becomes randomized, and as recent 3D simulations show, the magnetic field possibly becomes somewhat turbulent as well. Then there is another boundary over here, which is really a forward shock. In that sense, this shock front can be called as a reverse shock, or more often it's called a termination shock. And somewhere there is a forward shock where there is an interface with the ambient interstellar medium or ejecta in the supernova remnant, if this pulsar wind nebula is young enough, right? So those are basic zones, and downstream of the shock, of this termination shock, we have a really magnetized plasma, and we have highly relativistic particles in this plasma. So you'd expect at least these two important emission processes happening, the synchrotron and inverse Compton. I will primarily in this talk focus on this process. So once we know the emission process, the quite simple estimates, but useful ones, can be made. So for instance, if I parameterize these equations using magnetic field in this region and the Lorentz factor of the particles, I can write down the energy of the synchrotron photon. I can actually write down the energy of inverse Compton photon as well through the energy of synchrotron photon eliminating gamma, for instance. But I'm not going to need this equation in my talk today. And then one can actually estimate the characteristic size of this wind bubble by a very simple argument by saying that the pressure of this relativistic wind, which is really given by E dot, by spin down rate of the pulsar, should be equal to the ambient pressure, whatever it is inside the supernova remnant or somewhere outside there. If you plug in reasonable numbers, so this is a young pulsar, this is sort of typical pressure inside maybe supernova remnant, which is a few kiloyears old, then the size, the expected size is a fraction of a parsec for this bubble. But it's really an order of magnitude estimate. It can be a factor of a few different, right? So then one can estimate the synchrotron cooling time, how long these bubbles of synchrotron emission that we see in X-rays. That's why we actually change parameterization from gamma Lorentz factor to energy of an X-ray photon. How long they will live, how long can we expect to see them, and that's going to be on the order of kiloyears. Right, and it's again very much order of magnitude estimate. So one typically parameterizes the luminosity of the observed pulsar wind nebulae, introducing this efficiency, radiative efficiency, that is just a coefficient between E dot and the actual observed luminosity. So there is surprisingly very large range of these efficiencies based on current observations of pulsar wind nebulae from 10 to the minus 5 to 10 to the minus 1. Right, this is another picture which is more recent. I stole it from the website called Astrobytes. Someone drawn a picture of a pulsar wind nebula with a little bit more detail than Aharonyan did, which includes some interesting things like a collimation by the hoop stress of the jet and the backflow from the termination shock and so on. That's from recent MHD simulations. It also includes something that hasn't been shown, is that this interface and the forward shock. Yeah, really there's more detail there than I'm actually going to be able even to discuss, but I'll refer to some of these things that you saw in those pictures later in the talk. So there was this a big step forward in terms of studies of pulsar wind nebulae, which came with the launch of Chandra and XMM Newton. So, of course, everyone by now knows what are actually these observatories, what range of energies they're observing, and how great is the resolution, really comparable to the resolution of optical telescopes, 0.5 arc seconds for Chandra. For XMM, it's not, maybe so good, but it has much larger collecting area, a larger field of view, but also the other disadvantage is a higher background. So, both, of course, observatories are useful, but Chandra is particularly useful for compact pulsar wind nebulae or faint, very faint pulsar wind nebulae. So by now, if you count all these little tiny faint pulsar wind nebulae, probably around 100 pulsar wind nebulae have been detected in X-rays, right? And then more recently, there is also a hard X-ray telescope, NuSTAR, that has also poor resolution, worse than XMM, but it goes to higher energies. Right, so I will primarily focus on what we have learned with Chandra in this talk for the reasons I explained. In particular, the things that were actually enabled by Chandra and XMM, the ones that are relevant for pulsar wind nebula science, is the high-resolution images which actually reveal the fine structure of pulsar wind nebulae, and I will explain in my talk why this fine structure is important, why it's not just some kind of incremental details, and the Rosat images would be sufficient. It's not. There is a lot of interesting physics hidden in this fine geometry there. Then with Chandra, it's possible to do spatially resolved spectroscopy with ACES. That means we can actually study how the particle distribution evolves with the distance from the pulsar in different directions. That's also important because winds are anisotropic, right? Then what's possible with Chandra is actually resolving very faint sources. And that helps in, let's say, I give one example. It helps when you say looking for a potential explanation of the TeV source and you're finding some resolved source and you are able to actually classify it as a pulsar wind nebula. That's only possible with Chandra. So there's sometimes subarcsecond localizations allow to discover compact objects that turn out to be pulsars. I'll give an example later through multi-wavelength observations, right? So localizations are very important, subarcsecond localizations. And also being able to disentangle different spectral contributions, for instance, thermal emission from supernova remnant, from non-thermal, from the pulsar wind nebulae, is really can be done with Chandra very well and with XMM to some extent, but it was already mentioned by Pat and Samar. Right? The other demonstration of how much progress was made with the launch of Chandra and XMM is possibly this graph of articles that are written on pulsar wind nebulae as a function of time. And that is about the time when the Chandra and XMM were launched, right? So there is a big growth there. So again, just remind you how the pulsar wind nebulae looked like before, and that's how they look after with the Chandra. So we recognize some famous ones. The ones from the previous slide, the Crab and the Vela pulsar wind nebula are here, right? Then this is the other one shown before. So this is just a gallery. It's not incomplete actually, and there are all kinds of shapes you can see here. And rather than just being a zoo, it's actually, there is a very important information encoded here, and I'll try to explain how this information can be used later in my talk, right? So basically, this information is encoded in the shapes and orientations of pulsar wind nebulae. So you can see that many of them have toroidal and polar components, which are sometimes called just toroid, jets, or rings, whatever. So that carries information about orientation of pulsar spin axis with respect to the observer's line of sight. And then I also believe that there is an information here that is encoded about the angle between magnetic and spin axis. So I'll talk about it a little later in detail. The other important factor which affects the appearance of the pulsar wind nebulae is the properties of the ambient medium, right? What's the pressure, for instance, of the ambient medium? Is it uniform medium or non-uniform medium? Is there reverse shock or not? And actually, the last important factor that I would like to mention is the Mach number that corresponds to the ratio of the pulsar velocity to the sound speed in the ambient medium. Now, this Mach number can be also relevant in the case when you have a reverse shock coming and pushing on a pulsar wind nebula. Then it might be defined slightly differently. Right, so this is a demonstration of what happens when you have a low Mach number, like of less than 1, so subsonic motion, and the supersonic motion. This is a high Mach number. Of course, these are, they are not, these schematic pictures, they are not resembling the complex anisotropic pictures that you can see here. It's just like to demonstrate only one thing, is that the Mach number, large Mach number and supersonic motion distorts the pulsar wind nebula substantially. There's still those regions that you can still recognize in this picture, the unshocked wind with indetermination shock, the shocked pulsar wind, the contact discontinuity shock, ISM, etc. So the regions are still there, but the shape is distorted. Now, if we put a really realistic anisotropic wind, this picture should become more complex, of course, right? So let's recall that the typical pulsar speed, just based on the measurements, is of the order of few kilometers per second. And of course, there is a distribution there. Now, the typical speed of sound in the ISM can be estimated like this. This is a warm ISM phase, so it's about, let's say, 10 kilometers per second. So you can see that subsonic motion is really only possible for pulsars that are still in their host supernova remnants, right? So the younger ones, or the ones that were not kicked so much during the supernova explosion. If you wait long enough, or if the pulsar is kicked fast, it will will be moving in the normal ISM, and it has to be supersonic motion, therefore, right? So let's consider first the case of more or less isotropic pulsar wind nebula in supernova. There we can use this estimate to estimate the size, right? And that gives that 0.2 parsec that was shown before. And this is an okay estimate for that case when you have a pulsar in the supernova remnant. You can still use similar kind of estimate by acquainting pressures for supersonic case, but there you have to add the pressure, the RAM pressure to the ambient pressure, and it will become dominant there, right? Just to show some more images, actually zoomed in images of the pulsar wind nebula that actually have been studied in detail. So they are kind of collected in this slide and in the next slide. What does it mean? It means there was a dedicated long Chandra observation, or the pulsar wind nebula is so bright, well, like in case of the crab, that maybe you don't even need long Chandra observation, but it's either of those two. So we have good data on most of these nebulae. Well, there is some improvements maybe needed for a couple of those, but we have a pretty good data for these ones. And that's why I will focus next on these nebulae. So these were the pictures, and that's the same well-studied pulsar wind nebulae collected in a table. There's about 18 objects, I believe, here, right? And the details, the exposures, and the total fluxes are here. So, of course, the first one is crab, right? There's a lot has been said already about the crab, so I'll go very quickly. This one is a torus jet-type pulsar wind nebula. It's obviously not supersonic with respect to the environment of supernova remnant. So remember those words because they will be important. The ring, the inner ring, right? The torus and the jets. The spin axis coincide in this case with the velocity vector because it was measured how it's moving. And the inclination angle, I will explain what's this zeta angle a little later, but this actually it is the angle between the line of sight and the spin axis of the neutron star. So that's this zeta angle. So it's 60. It's possible to measure this angle because you have this ring that appears as an ellipse, and it is becoming ellipse due to the simply projection effect. So we assume that it is actually a ring. So then you can get this angle, right? So it's interesting to study this structure. There's lots of detail. So let's just mention the jets. So according to most recent simulations, the jets are actually formed by the backflow from the equatorial outflow towards the pulsar, where there is a hoop stress that actually forms the jet, and those are the references, right? So, but if you look at the torus is really complex. It has all this fine structure, which is called wisps. So those are motions in the torus that you can clearly see here. These are not the only motions in the pulsar wind nebula, because it happens that on somewhat larger time scale, this jet is also kind of wiggling. It's actually the motion of this jet is sort of consistent with a rotating helix and the time scale of a few year time scale. So you can look at the Weisskopf papers, right? So this is another pictures of the crab, which are interesting. So this is somewhat perhaps better demonstration of the wisps. It's of the wisps moving in X-rays. So this is X-ray observations, right? And so this is multi-wavelength image of the crab at the done with JVLA, Hubble, and Chandra. So what's interesting in this multi-wavelength image? Well, first of all, you can kind of see three jets, really, if you look at it, different colors, different wavelengths. So it's kind of odd to have three jets in a pulsar. One could be part of the filament that goes like that, but the other two are actually not sure how to explain too. Then if you look at the multi-wavelength image, what one can find is that these wisps, they do not coincide in contemporaneous observations at different wavelengths. At different wavelengths, they're slightly different places. And that is still, I think, remains to be established. Why? Thankfully, we can actually track these wisps very good, and thanks to HST. This is not the YouTube movie. That's the movie that I made from the HST ACS images that were obtained during a later campaign than that movie. So here you can see that some of the wisps are not moving. You can actually measure how they slow down with the distance from the pulsar. The velocity field possibly can be reconstructed here, but that's a topic of another talk, right? So there is also a lot of information still in the archival data, if you like, because there's this filter that avoids bright filaments. And there you can see the counter jet of the Crab pulsar better. We have recently obtained also ALMA images of the Crab nebula. They're not very good because it was done during the very early phase. But anyway, you can see still the torus, this wisp region at the 100 gigahertz very well. And you can see one of the two jets and what I think is a filament, but not the third jet. Let's go through a little bit of observational review on the other very interesting nebula, which is Vela nebula. So this is a little older pulsar, also in the supernova remnant. So if a Mach number is larger than 1, it's not by much. It's probably of the order of 1. There is an analogy to Crab because it does have some kind of equatorial component and it has polar outflows. Although equatorial component looks quite different here. It's a kind of double ring structure. So it's different from Crab, where all these rings and wisps, they kind of seem to be in the same plane. Here you have two planes, maybe one below and one above the truly equatorial plane. So why is that? Possibly it's related to a different magnetic inclination angle. So the angle between spin axis and magnetic dipole axis, that would be the simplest probably explanation put forward by Helfand yet. What else is here different from the Crab is that the Vela really kind of features inner and outer jets. So in the Crab, you can't really make this division. It's jet, single jet becoming fainter as you go along the jet. So here, what we call inner jets, they are much brighter than the outer jet, in particular this jet. And then there is some interesting asymmetry, is that this inner jet is brighter than this one, but this outer jet is brighter than the other one, right? So that's maybe implies that there is some bending in three-dimensional space going on as you go further away from the pulsar. And some of this bending we can actually see in the movies that I will show soon. Then there is this interesting structures at the base of the jet, possibly related to this hoop stress collimation of the backflow that I referred previously. So, but it's still unclear why there is such a drastic contrast between inner jets and outer jets. We cannot really see motion, steady motion here in this torus. There are some indications of variability, but not like we can resolve wisps that are moving in the torus, right? So we can't directly perhaps measure this motion, but we can measure motion in those jets, and then I'll show how it looks like. Well, the standard synchrotron brightness estimates can be used to get the estimate of the magnetic field and the electron energies. What's interesting, though, is actually to add radio to this picture. So the radio is blue, the X-ray is now red. There's a complete anti-correlation, if you like, or the complete lack of correlation between X-rays and radio. I'll be just very brief. I think it implies that there are two different populations of particles, two different SEDs there, because there is very similar spectra of these outer jets and this compact nebula. The spectra are very similar. There is absolutely no radio counterparts to these X-ray jets. Rather, the radio emission comes from these lobes. And these lobes are not completely devoid of X-ray emission. Actually, interestingly, there is a harder X-ray emission with harder spectrum that is kind of faint, but it fills this lobe. And there's a very sharp boundary here. So I don't know, one possibility to explain this is that there is this crosswind from here, some motion within the supernova remnant causing another shock here, and there may be additional acceleration going on in this area producing different spectrum. I think it's an interesting possibility discussed in Bykov et al. 2017. Now I promised to show some motions and that the jet is actually, does something, some bending. So it does look really like a rotating helix, if you like, and obviously it has to be three-dimensional, so it is possible that it has a bend toward the observer, but why it is always stays brighter than this outer jet over here, it's not clear. Now, what's the reason for this apparent rotating helix? Well, there can be two really reasons. One is the kink instability that is kind of persists there and behaves in more or less regular way for some time, the time that we observed, or there can be actually a precession of the source of the jet of the neutron star. I'm not going to go in that possibility. So the inner nebula is also variable, but there's no time to quantify those details there. Now I mentioned that the spatially resolved spectroscopy is advantage of Chandra. And here we can really study the structure of the nebula in a spectral map. So this is a photon index, and you can clearly see the very hard inner nebula, the hard jet over here, and then there is this harder region over here, and actually there would be another one there, but not well shown, right? So there is anisotropy, clear anisotropy in how the SED behaves, right, with a distance from the pulsar. So that should be taken into account because very often things are really averaged around this angle. Now, I don't have time to show any other spectral maps, but we have done spectral maps for all these pulsar wind nebulae that are well observed by Chandra, and that allows us to measure the spectral indices in the sort of innermost region close to the termination shock, so hopefully there's no effect of cooling. Maybe it's a truly injected spectrum there, right? So if you take it like that, then these numbers may be more interesting. So you can convert photon index into a slope of the electron SED very easily for synchrotron. And so whichever you like, the slope of SED or the photon index, it's either that or that you can look at. You can see in terms of the slope of SED that there are plenty of pulsar wind nebulae with injection indices that are below 2, and I'll leave theorists to comment further on that. Now, is Crab and Vela the only temporally variable, like varying with time nebulae? No. For instance, there's one nebula here that we have started to study a few years ago. We obtained 3 images at different epochs, and there's clear change in the morphology of this nebula. So there's another Chandra observation series actually approved, so that will be more interesting to discuss when we get those. But it's a clear motion of that possibly jet feature. Now, if you actually add all of these observations and you zoom out, there is an interesting extended fainter structure on larger scales here. Why is it interesting? Because it kind of has a sharp boundary here implying some other shock at the larger distance, and then there is interesting extension here. You will see those extensions in supersonically moving pulsar wind nebulae. We call them misaligned outflows. I'm not sure if that one of those, but it's a peculiar thing. Now, if you put it in the multi-wavelengths perspective with the radio together, so we unfortunately do not see any radio from this region. There's plenty of supernova remnants, but the nebula itself is not detected. There's a TeV source here, and it yet to be remains to be understood how these two are related, given that sharp boundary over there. The other nebulae that I think are very interesting, that are emerging from these very deep observations with Chandra, is this one. So this one, if you look with Chandra, you can actually see a very faint ring over here, which allows you to measure the tilt of the spin axis to the line of sight. It's also variable with time, this nebula. And the other recent work found this little jet, which is again looking like a helix. So we don't see how it rotates or precesses, but it is a nice helical jet. Now, as I promised, Chandra can also deliver some very faint nebulae that you otherwise wouldn't find. And there's probably plenty of those still in the archival data. So this is just an example of Chandra observation where we studied this pulsar. So it was designed to observe this pulsar, and next talk by Noel Klingler will address that nebula. However, by accident, we found this extended source over here, right? It's a really tiny, faint extended source with the central source. There's not so many extended sources that you find in X-ray images of that kind with the bright source in the middle. It could be AGN, but there's nothing in the radio or optical. Then we concluded it's a pulsar vein nebula. And then we recently found a paper that is very recent, that there is actually a gamma ray pulsar was just discovered right there. So, but basically just using Chandra, you can find it and say that it is a pulsar vein nebula. There is a lot of work to be done still. So the other sort of topic that I would like to talk for 5 minutes perhaps is relating the pulse shapes and pulsar vein nebulae morphologies. You should forgive me, I will be going really quickly through the pulsar light curve terminology, sort of, because of the lack of the time. So I will basically say that there is a rotating vector model everyone probably knows here. There's many angles that can be used there, but two most important angles is the angle between rotation and magnetic axis, or let's call it a magnetic inclination angle, just for shortness, and the other is the viewing angle, right? So those are the two angles between the line of sight and the spin axis. So then there has to be some assumptions made about where the emission comes from the pulsar, from what regions of magnetosphere, before we can compare make sense out of the light curves, right? And so there has been a lot of work done here. I cannot go through this, but the radio emission still probably comes close to the pole, right? Close to the magnetic pole, and it may be a complex region which is like a hollow cone rather than a pencil beam, but there's no time to discuss that. And the gamma ray emission comes from the outer magnetosphere, perhaps close to the light cylinder. So that's all I'm going to say about that. Then there are some conclusions that are kind of robust, maybe even regardless of the exact model of magnetospheric emission, right? So that single radio pulse and weak or no gamma rays imply that the line of sight and magnetic dipole axis are close to rotation axis. If you see strong gamma rays, no radio, maybe you're probably viewing orthogonal rotator at some substantial angle with respect to rotation axis. Orthogonal rotator means alpha is 90 or close to it. And then there's also, one can continue and say that if you see two wide, well-separated peaks in gamma, then this viewing angle is 90. If a single peak, 45, then this angle is 45, and so on. So it's basically, there is dependence also on the alpha angle here, which is not mentioned. So this is more complex than I just described, but these are sort of basic features that can be expected from the light curves. Now, that's how complex it gets. One can produce detailed maps of how the emission looks like with rotation phase and viewing angles. So if your line of sight crosses here, you will see two peaks in gamma rays, one here, the other is here. If it crosses line of sight somewhere there, then you wouldn't see any gamma rays. So people do that. They plot, they try to infer from gamma ray and radio light curves these angles, zeta and alpha, viewing and magnetic inclination angles. That's basic. The color coding is showing how many peaks you have, what's the separation between the peaks. These are different kinds of models produced by different groups. I'm not going to explain that. I just want to say that with the growing sample of those nebulae where you can resolve this fine structure and constrain zeta angle, one can actually constrain better those magnetospheric emission models, right? So, and one can maybe even use the relative strengths of equatorial and polar components in the pulsar vein nebula images to constrain the alpha angle, magnetic inclination angle, right? So for which nebulae you can do it? Well, let's say for these ones where you can find these structures such as jets, rings, tori, those things. And so when you start putting things together, I think it's really helps those people which model magnetospheres. It also can go the other way. So sometimes you cannot understand the structure of the nebula, but you have that gamma ray light curve from which you can go the other way and try to predict, explain what you see in the pulsar wind nebula. So this is just an example of if you make conclusions about these angles from the images of the pulsar wind nebula and you plot it on top of those pictures produced by light curve modeling community, those are the allowed regions. Now I'm going to kind of quickly scroll through the rest of these examples where you can infer angles from both light curves and pulsar wind nebula images. I'm just going to demonstrate that these are quite different light curves sometimes. Like in this one, you have a strong jet relative to the torus. The torus is very weak. You don't have a radio pulse, and so in my view, maybe it means that you have relatively small alpha, magnetic inclination angle. Here is clearly you have a very small zeta angle. The torus, it looks like a ring, not ellipse, right? So that may be helpful. What's interesting also is to look if there is any change in the spectrum of the nebula as a function of the alpha angle. The supersonic nebulae I'll leave to the next talk by Noel Klingler. So this he will show the images of the population. He will focus maybe on 4 or 3 objects, but there is like 20 supersonic pulsar wind nebulae which have an extremely interesting, recently discovered misaligned outflows. And in these cases, you can also use the structure of the compact nebula to infer the geometry of the pulsar and magnetosphere and to compare to the light curves. But Noel will talk about it. And in the remaining 2 minutes, George, I will very briefly show an example of the exotic system. So one is binary. In this binary, we just discovered the transient pulsar wind nebula as 2 series of observations. This is B1259, high mass binary. So we continue monitoring this. More observations will happen. Why is it interesting? Because the speed of this clump is like 10% of the speed of light. And it must be moving in a very rarefied medium. Actually, it has to be a pulsar wind. So this clump, which is probably some material from the decretion disk of the star, is actually launched into a pulsar wind and goes with a pulsar wind flow. I'm not going to go through these estimates. There are a couple more systems that are promising in this respect, and they will be observed soon. And the final slide is another exotic case of the pulsar or magnetar wind nebula that was mentioned actually already here, so I don't have to say much. But what I would like to say is that there is no doubt it's a nebula because we see it long after the flash of the magnetar, so it's not a dust halo. And moreover, it's persistent in the sense that in the very old Chandra observation from 2006, the flux of the nebula is about the same as in this recent XMM observation. So it can persist for very long, and therefore it's a way to find transient or dormant magnetars, perhaps. So finding those faint extended objects in existing Chandra data is important. And here is my conclusions. I'm just going to leave it here because of the lack of time. Thank you. Sorry, George.
Thank you, Oleg. What are the questions? Sergey.
Just about the last slide with the magnetar and nebula. Is it clear now if this nebula is powered by rotational energy losses or magnetic energy losses, or both are possible?
I think it has to be powered by magnetic energy. The question that remains there, in my view, others can disagree with me, but whether it is actually was produced in some kind of cataclysmic event that we did not register, and it still lives and slowly may be changing, but too slow for us to see how it's changing, or is it sort of a persistent phenomenon that was always there since the birth of that magnetar that I don't know.
Other questions? Okay, I do not see any, so let's thank the speaker again. And the next speaker is Noel Klingler of George Washington University, who will sort of continue the talk by Oleg, and the title of his talk is Deep Chandra Observations of Nebulae Produced by 3 Supersonic Pulsars.
Hi, everyone. My name is Noel Klingler. I'm a 5th-year grad student from George Washington University in D.C. Can everyone hear me okay? All right. Before I begin, I'd like to thank my advisor, Oleg, and my collaborators and the conference organizers for this opportunity to present my research. So today I'll be talking about deep Chandra observations of the nebulae sonic pulsars and the long extended tails and other features they produce. A brief overview of what I'll be talking about today is basic properties of supersonic pulsars and their supersonic pulsar wind nebulae. The 3 objects of interest today, J1509, 5850, not to be confused with B1509, 58, which is a different pulsar. There's a poster of it in the poster session if you want to see that one. B0355 plus 54, and J1747 minus 2958, or the mouse. Then I'm going to be talking about compact nebulae morphology, and then the connection of that with pulsar geometry and light curves. Misaligned outflows, which are these puzzling structures seen in about 4 supersonic pulsars in recent years. Then spatially resolved spectroscopy of the tails and how we can infer properties of the tail from it, and then a comparison of pulsar tails and the trends we see. So the most important factor in determining a pulsar wind nebula's morphology is the Mach number, which is the ratio of the pulsar's speed relative to the speed of sound in the interstellar medium. Theoretically speaking, if your pulsar has a Mach number lower than 1, you'd get a spherical pulsar wind nebulae, but we don't really see that. We see jets and tori because the wind is mostly anisotropic. If your pulsar has a Mach number greater than 1, you would expect to see termination shock here, which inside the unshocked pulsar wind you wouldn't see any emission, and that's right there in the inner ring of the crab. Outside of the termination shock, the pulsar wind becomes shocked, and you would see synchrotron radiation from radio through gamma. And then the contact discontinuity separates the shocked ISM, interstellar medium, from the pulsar wind and confining it with its pressure. Here's some examples of tails. So supernovas typically give pulsars a birth kick on the order of 400 kilometers per second, although some are as slow as 50 and some are as fast as 1,000 kilometers per second or more. So this means pulsars usually escape their supernova remnant within a few tens of kiloyears. ISM speeds of sound can vary from a few kilometers per second to a few tens, even 100 in some cases. So typically Mach numbers are on the order of 1 to 10, although they can be higher. Supersonic pulsar wind nebulae consequently usually display a bow shock compact nebula, which can take many different forms, and sometimes a long tail, although not all show tails, and sometimes some show a tail without a compact nebula, so that's also another thing. There's about over 230 pulsars now whose proper motions we've measured. There's about 30 fast-moving pulsars who have pulsar wind nebulae seen in X-rays. Fewer are seen in radio, and that's usually because only pulsars with under 1 megayear have enough spin-down energy to produce nebulae. Morphologies are highly varied. We see here that have filled morphologies, some that display the opposite, hollow ones, a combined compact nebula and tail. Some are asymmetrical. Some don't have a compact nebula but have a tail behind it. and then various other less certain morphologies. The first object here is J1509. It's about 3.8 kiloparsecs from its dispersion measure. It's middle-aged, and we estimate its velocity to be on the order of 400 kilometers per second. It's seen in radio and gamma rays, and this long 370 ACIS exposure reveals its highly collimated X-ray tail, but it also reveals this long structure ahead of the pulsar's direction of motion. It kind of looks like a headlight. It's one of the examples of a misaligned outflow. And then on the small scale, you can see what looks like two jets, and you can actually, we have 4 separate observations spaced a couple months apart, and you can actually see blobs of plasma moving along the jets at about 0.3 C, which is like similar speed seen in the Krebs blobs along the jets. And here's a radio image. It has a radio tail coincident with the X-ray one, except that there's no radio emission near the pulsar except for the pulsar emission. The radio nebula brightens with distance, and then it fades and narrows. BO355 is a lot closer. It has a parallax distance of 1.04 kiloparsecs and a proper motion of 61 kilometers per second, thus putting its Mach number between 6 and 60. It's a little bit less energetic, and it's not seen by Fermi, and there's no radio tail associated with this. There's been a bunch of searches with the VLA and the JVLA, and nothing was seen, unfortunately. But this deep exposure reveals this very well-defined bullet-shaped or mushroom-shaped compact nebula, which is bright along its central axis. It has this drop in brightness there, and it has about a 2 parsec long tail that kind of bends slightly here, and then there's hints of a misaligned outflow, which I'll talk about later. And the last one is J1747, the mouse. Its distance isn't very certain, but it's on the order of 5 kiloparsecs. Its proper motion has been measured, and at 5 kiloparsecs, it's 300 kilometers per second. Its spin-down age suggests 25 kiloyears, although it's probably on the order of 50 to 100 kiloyears, since no associated nebula is seen in radio or X-rays. It's also seen in gamma rays as well as in radio. And it features this filled morphology similar to BO355. The X-ray nebula narrows with distance, and then it has this extremely long 17 parsec radio tail that initially widens, but then it kind of narrows. And I think it's one of the longest pulsar tails seen. So the compact nebula morphologies can appear to contrast, but 2 examples of that are Gaminga and BO355. But Gamingo is almost totally radio quiet except for very low frequencies, and it's very loud in gamma rays. BO355 is not seen in gamma rays, but it's very loud in radio. So we can interpret this as that we are seeing Gaminga edge on, and that this is its equatorial outflow crushed by the ramp pressure and pushed back, and that these are the jets. Now, if you can imagine, if you looked at Gaminga from above the equatorial outflow, you would see something similar to this. And that's the nebula, and then these 2 things moving away from the pulsar and separating are the jets superimposed on each other in projection. So there's as Oleg said, there's a connection between the pulsar wind morphology and the light curves. The geometry of the compact nebula can be used to obtain reviewing angles. For example, if we assume that this fall in brightness in the mouse compact nebula is similar to that of BO355, we can use a geometry of that to estimate that we're looking at this from above 20 degrees above the equatorial plane. In which case, because we also see the radio pulses, that would give it a similar magnetic offset angle on the order of 70 degrees. We see similar angles for J1509 based on the fact that its light curves in radio and gamma rays are almost identical, not only in morphology, but also in the separation between radio and gamma ray peaks. And that can help us discern less certain pulsar morphologies, like now we know that the mouse is equatorial outflow dominated and that there are no jets, even though we're viewing at it from a similar angle. And also, combining the X-ray images with these light curves can help reduce redundancies in constraints from looking at the gamma ray light curves. Why isn't that it? Oh, here we go. Okay. So, compact nebulae. The simple isotropic MHD simulations don't always describe what we see here. In the case of BO355, they do, but it doesn't fully capture the anisotropic winds and the misaligned outflows. Also, in many cases, the velocity vector of the pulsar appears perpendicular to the velocity vector, although there are some examples where it's offset or somewhere in between aligned and anti-aligned. And this challenges previous hypotheses of spin velocity alignment, and it can provide clues on pulsar birth kick mechanisms in their progenitor supernovae. So, in recent years, a couple of these puzzling misaligned outflows have been seen. The first one is seen in the Guitar, the second one is seen in the Lighthouse pulsar wind nebulae, and then we've found two more cases, and then recently a fifth candidate has been found, although we don't really know about its velocity yet, so it's tentative. But at first it was believed that these are the pulsar's jets, but that doesn't really work out that well because pulsars with these kind of speeds, their jets would bend on very small, almost arcsecond scales. And also in these two pulsars, we can see the jets, so these definitely aren't the jets. So Bandiera, to explain the Guitar, suggested that in high Mach pulsars, the bow shock standoff distance becomes smaller than the electron gyro radius of high-energy electrons. So then the high-energy electrons can't be contained within the bow shock and can then leak out into the interstellar medium where they travel along the ambient magnetic field lines. Other theorists have said that for supersonically moving objects, not just pulsars, some galaxy clusters do this, but the ambient magnetic field lines can drape around the bow shock, and the deep images of the Lighthouse pulsar wind nebula kind of confirm that, because you can see this outflow bend, but then bend back as if it's draped around the bow shock. And Bikov et al., to explain the the asymmetry in these, has suggested that the interstellar magnetic field lines can reconnect with magnetic fields in the pulsar wind nebula bow shock or jets, which will allow high-energy particles to be launched along the interstellar magnetic field direction. But because the ISM magnetic fields can only reconnect with the magnetic fields that are oppositely oriented with them, it explains why one side is highly favored than the other. Obtaining the spectra of the BO355 nebula, the compact nebula is hard, but right as you cross over this brightness drop, the spectrum becomes about 1.7, and it stays that up to 2 parsecs down the tail. So that suggests that there's no significant cooling happening along the tail. We model this tail with a simple 1D synchrotron cooling model from Chen et al. It has drawbacks in the sense that it assumes a cylindrical tail and a constant width, flow speed, and magnetic field. But our data suggests either a very fast flow speed on the order of a few tens of thousands of kilometers per second or a very low magnetic field. But the lack of cooling could hint at some kind of particle reacceleration mechanism playing a role here. The J1509 tail, some interesting things happen here. Initially, gamma softens in X-rays moving down the tail. The radio tail expands, as well as the X-ray one, and increases in brightness. And this is radiopolarimetry showing the magnetic field orientation along the tail. And it's initially perpendicular to the tail axis. But then halfway down the tail, the spectra starts to harden. The magnetic field reorients and becomes parallel to the tail. And the radio tail fades, which is interesting, as well as it narrows. But you would think that if it's narrowing, it should increase in brightness because the particles are being confined to a smaller area. The misaligned outflow cools, which suggests that it's not the same type of outflow as a tail. And the magnetic field also kind of decreases in the second part of the tail somewhat drastically, which suggests that maybe there's some kind of reconnection here. So the Mouse pulsar wind nebula in X-rays is bright enough that we can produce an adaptively binned spectral map of this one. And that allows us to create regions of equal signal-to-noise ratio, which maximizes the spatial resolution for a certain signal-to-noise. And we see here there's rapid synchrotron cooling over a 45 arcsecond extent. Gamma almost doubles from about 1.6 to 3 over this extent. However, if we extract the spectra from the entire tail behind the pulsar, it fits a very well-constrained single power law model. And that's strange because some of the power laws is not a power law in itself, but here it fits very well. And if we didn't perform spatially resolved spectroscopy, we'd think, oh, that's the spectrum of the tail. But this highlights the danger in obtaining the injection spectrum from large extraction regions and shows that it's best to use a gamma of the uncooled wind near the vicinity of the pulsar. Similar rapid cooling trends are also seen in the Lighthouse pulsar and nebula. So we plotted the X-ray spectrum here and then the VLA spectrum, and it indicates some kind of spectral turnover around infrared. So we checked the Spitzer MIPS 24 micron data, and we see a point source where the pulsar is. I don't know if you can see it very well in here, but there are other 2 mass sources circled in green, but there is no source anywhere near the pulsar. And it's definitely not thermal emission from the neutron star surface, because that should be orders of magnitude lower for a pulsar at 5 kiloparsecs away. So the flux from this area kind of fits right on the extrapolation from the X-ray spectrum and also from the lower frequency radio spectrum. The low frequency spectrum has a gamma of 1.2 plus or minus 0.1, and the spectral turnover here is about 0.9. But usually in other tails where we see radio emission, the spectral turnover is about 0.5, so that is interesting here. But using both the low frequency and high frequency spectra, we can estimate the magnetic field in the X-ray tail to be on the order of 300 microgauss, which is quite high. And that also, if this is true, suggests a very low flow speed here on the order of 1,000 kilometers per second or less. And that would explain the rapid synchrotron cooling seen here. Also, radiopolarimetry of the mouse suggests that its magnetic field is aligned parallel to the tail, at least in the near vicinity of the pulsar, which is the opposite of what we see in J1509. So, in summary, cooling trends can vary. You can either have no cooling, rapid cooling, or even reheating or reacceleration parsecs away from the pulsar. And this could be because of different magnetic field strengths, changing flow speeds, or magnetic reconnection. The tails can widen with distance, so they can become narrower, they can bend in some cases, and dim and brighten, and this can reflect different ISM densities, temperatures, and pressures, or entrainment of ISM matter, like it being pulled into the tail. So that studying these tails allows us to probe the interstellar medium better. Misaligned outflows, they're asymmetric, seen at very different angles with respect to the pulsar velocity vector, and they're likely caused by particle leakage from the apex of the bow shock into the ambient magnetic field. But these structures are rare, only 4 or 5 of them are seen, and it's not clear why they're so uncommon or far less common than tails are. The magnetic field orientations and structure can vary. They can even switch, and it's not clear how the magnetic field structure in the tail depends on the spin velocity alignment of the pulsar. Looking at this small sample suggests that there isn't a very clear relation on the two. And lastly, X-ray images of pulsar and nebulae can be combined with multi-wavelength timing data to place constraints on the viewing angle and pulsar magnetosphere and geometry. So that's the end of my talk. Thank you. Are there any questions?
Thank you, Noel. Nice talk. You finished it in time, which is also important.
Nice.
Please, questions. No questions at all? Okay, then thank the speaker. Yeah, I figured it out, thank you. Huh? It's your back, very good. I am truly glad.
Thanks.
Okay, the next talk is Dr. Tanaka, Confinement of Pulsar Wind Nebulae by their supernova remnant and magnetic dissipation.
Today I'm talking about this title. Okay. And so I'm talking about the pulsar in Nebula. So of course you know the pulsar in Nebula is powered by the pulsar, and this is the PP diagram of the pulsars, and the red ones are the red points are the pulsar with observed pulsar in Nebula, and only these parts can be found because these have the light spindle luminosity. So so pulsar in Nebula have the broadband emission from radio to gamma. This is the spectrum crab for blue and crab pulsar for the black. And so the pulsar emission is only a few percent of the spindle luminosity, but the emission from pulsar nebula is much larger than the pulsar from the pulsar. Okay, but we don't understand the nature of the pulsar wind. Okay, so the structure of the pulsar nebula is a bit complicated because at least the 5 distinct regions, and the most innermost region is the pulsar, and divided by the right cylinder, and this is called magnetic sphere pulsar. And the plasma collected around the magnetic sphere flows away from the pulsar, and this outside is called pulsar wind region. It's considered the plasma moving about speed of light, and on the other hand, the outside is just the medium or the supernova ejecta create the pulsar. And the pulsar wind is collide with this outer medium and create a shock at here. And we observe the shock the pulsar wind here. And this region is pulsar nebula we saw in X-ray, and this is the compressed image, so including the radio and electricals. And the crowd, okay. So this is just the introduction, and I'm talking about the sigma problem. So I review the sigma problem by kernel quantity. So, but essentially, so this is already stated by this recent Gantt paper. And so, what is the kernel quantity model? It's that this is the model for the Crab Nebula, and they consider the pulsar wind is the cold magnetic electrophoton flow from central pulsar, and ultra-relativistic. And so they consider the steady and spherical symmetry of the system, and they consider the standing strong shock at the inner ring. Inner ring is this ring. And they also consider that the pulsar nebula is the post-shock flow of the pulsar wind. Yes, I already mentioned that. And they assume the ideal MH flow and the pure radial flow of the pulsar wind nebula flow, and pure toroidal magnetic field of nebula flow. And so the broader the emission observed from the nebula is from the particle accelerated at the tangential shock. Okay. So there are only a few parameters to control the system, and the most important parameter is the magnetization parameter sigma. This is the flux ratio of the particle and the energy flux ratio of the particle and electromagnetic field in the upstream of the temperature shock. Okay, so as the first paper of the general quantity, they consider the dynamics of the Parseval's nebula. And so we know that the pulsar itself should have a much larger sigma, because they are just a first approximation, just a rotating dipole, and they create a prism around here and this accelerate and may decrease their magnetization. But however, the Kenyan quantity found that so because the expansion velocity of the Parseval nebula is much slower than the speed of light, so we need a very small value for the sigma. So the expansion velocity of the Parseval nebula is found from like this. So sigma times c is the expansion velocity. So we need the sigma to be much smaller than 1. For this is the requirement from the dynamics of the Parseval nebula. And so small value of sigma is also required from the spectra. So by the second paper of the Kenyan quantity, they consider spectrum of the Parseval nebula. And so the Parseval nebula have a broadband emission from radio to TV, and the most important things is the spectrum peak at the optical wavelengths. So to explain the peak at optical wavelengths, so Kenyan quantity found that the gamma W is the Lorentz factor of the pulsar window upstream. It to be about 10 to 6, very large. And so if we change the value of this, so peak of the spectrum shift like this. So this is a large, 3 times 10 to 7. So we regard around this value. And also, after the recently, so there are many gamma ray observations for Parseval nebulae, and we saw that the synchrotron, the spectrum affected by synchrotron radiation for radio, optical X-ray emission, and gamma ray for inverse component radiation, and mostly the flux ratio for synchrotron component, inverse component is much larger than 1. So we require the small sigma from only from the spectrum. Okay. So the problem is how to reduce the sigma much larger than 1 to much smaller than 1. So this is called the sigma problem. And so what's wrong with the Cauchy model is we don't know, but so the Cauchy model is, we know that it's very simple because they assume the one dimension and static system and MHD model. So, but we know that the Parseval nebula is more complicated system. It did look like one dimensional, and so the study by there are some numerical study recently show that so this summation is MHD, but they say that we needed the magnetic dissipation to explain this structure, and so we also know that Crab nebula is not static system. Okay, so today I'm talking about so we include the effect of this turbulent motion of and the dissipation of magnetic field into the Kenyan quantity model, and we look for the solution to the sigma problem. Okay. So this is the model my model of my study, and this is just only the MHD equations for four forms, but a bit complicated, but just extend the Canyon quantity model by adding some phenomenological terms representing the radiation loss. So Canyon quantity did not include the radiation loss for the calculation, and turbulent magnetic field and magnetic dissipation. So these phenomenological terms are already introduced by these authors. These authors are using this phenomenological term to accelerate the flow in GRB outflow. But we use this same term for decelerate the nebula flow. And this is the equation of continuity. And this red terms are radiation loss. And this is the injection equation for the mean magnetic field, not turbulent one. And this is the injection equation for turbulent magnetic field. And we consider that so the pulsar window have the pure toroidal magnetic field, but some part of the toroidal magnetic field is converted to the turbulent magnetic field. So this term is to convert the toroidal magnetic field to the turbulent magnetic field. Okay, so and so turbulent magnetic field may reconnect and dissipate. So I put the dissipation term to the turbulent magnetic field equation. Okay, so but this is the four form. It's a bit complicated, but I write down the three form. And so this is the full equations. And these color, if we neglect what make zero to these colored terms, the equation recover the Canyon quantity model. So just the turbulent magnetic field part and this radiation loss and the conversion of the turbulent to toroidal magnetic field and dissipation. And we have the 6 variables, and there are six equations, and there are 4 parameters for this equation. But we set adiabatic index for the flow is set to the 4/3, and so synchrotron radiation cooling is set to the synchrotron radiation. And there are two parameters to represent conversion of the magnetic field to turbulent one, and the dissipation of magnetic field. Okay. And we also need the boundary condition for the system, but we are at the Canyon quantity model. So the boundary quantity, we only require the two parameters. So if upstream of the pulsar window is upstream of the thermal shock is we consider the cold magnetic red wind. So it can be written like this, and so because this is the Golden Hadrian, then number flux is written with also spinal luminosity. So we only need this kappa and gamma and sigma. This is the parameter to determine the property of the pulsar wind. And so if we give the spinal luminosity of the Crab nebula, so two of these 3 parameters give the full property of the pulsar wind. And setting strong shock, and we obtain the boundary condition for the nebula flow from the Rankine-Only relations. Okay, so now we have 4 parameters for the system, and we try to find satisfy the expansion velocity to be about much less than speed of light, is about 1,000 kilometers per second, and radiative efficiency of about 0.3. Okay, so this is the result. One of the result. So we set the multiplicity was 10 to 4, and this is the distance from the shock. Thermal shock is set to the radius for inner rings. And this is the for velocity. And the yellow, red, blue, green, it corresponds to the magnetization of 110 and 1 and 0.1. And this black line is corresponds to the Kenyan quantity model. So we fit the expansion velocity at the outside of the. Okay. And so to reduce because the for velocity is very fast for the large magnetization, but it's decreased with the distance from the shock, because we include this parameter. So conversion of the toroidal magnetic field to turbulent field can decelerate the flows. Okay. So for these values, we obtain this expansion velocity. And so to explain this expansion velocity, we don't need the dissipation of the magnetic field. But magnetic field dissipation affects the relative efficiency. So we also see the relative efficiency, and the color is the same. So 100, 10, 1, 0.1. And okay, so this is this sample shock, and this is the randomness defined like this. So the mean field and the turbulent field. Okay, so this is the value of relative efficiency here, and we need the value around here. So high magnetization, and this characteristic length for dissipation infinity means that no dissipation is favored for in this case. And for the randomness, so some observation of polarization, it shows that we require the randomness of magnetic field around like 0.5 or around here in close to the pulsar. So around this value is also good. And this red one, sigma 10 and infinity, is corresponds to this thick red line. But a little bit large randomness in this case. Anyway, so now we find that so large sigma flow in upstream of the time shock is allowed to explain both expansion velocity of pulsar nebula and relative efficiency. Okay, so this is the summary of my talk. Okay, we consider the deceleration of the relative magnetic outflow, and so both dynamical and spectral sigma problems are resolved by the model. It means that so high sigma flow at upstream of the time shock are allowed. Okay, and but the heuristic model of the dissipation and conversion is adapted from this paper, and disappearance of the toroidal field is important, but we do not need the dissipation of magnetic field in that case. But and for the small dissipation length scale and large value of the multiplicity, we don't show the different multiplicity case, but reduce the relative efficiency. Okay, so this is a further study for this problem. Okay, I finished my talk. Thank you.
Questions, please. Absolutely no questions, Sergey.
Sorry, the question is not related exactly to your main results, but in the beginning you showed this structure of the remnant, and in some cases there should be the reverse shock which interacts with the pulsar wind nebula. So the question is how actually many examples do we know when we see this interaction of the reverse shock and pulsar wind nebula?
reverse shock and particle nebula.
So it should be, somewhere here there should be a reverse shock interacting with the wind nebula. Are there any good examples of such situation from observation, or?
I don't know. So,
Possibly not in the crab.
No, not in the crab for sure, but in general maybe if.
the interaction. Sorry.
Other questions? Okay, I see no one. Okay, then thank the speaker again. Let's have a coffee break and be back in 20 minutes.
Yes.
Okay, let us start our last session for this day. The speaker is Sandro Mirighetti, and he will tell us about radio properties of the mode switching pulsar BO943 plus 10.
Good afternoon. I started into X-ray astronomy in the mid of the 80s, and I grew up with the idea that rotation power pulsars are basically the only steady, non-variable sources in the very variable X-ray sky. And I've been with this belief until recently, actually. But I will show you that things are changing. Indeed, there have been discovered recently a few exceptions to this rule. Some isolated neutron stars showing X-ray flux variations. One example is this XDIN, in which you see here flux variation in the soft and in the hard X-ray flux, and indeed this is a time of about 10 years, and you see that the temperature is changing, but we believe that this kind of long-term variation are in some way related to some kind of magnetically powered activity. Indeed, these kind of objects are believed to be the descendants of magnetars. Another example of variability in X-ray rotation powered pulsars are the bursts that have been observed in a couple of high B field objects. You see this very short burst resembling those of soft gamma ray repeaters and anomalous X-ray pulsars, coupled to an enhanced X-ray emission. Again, this is something that occurs in a rotation-powered pulsars, but is probably related to, again, some kind of magnetar-like activity. On the other hand, in the radio band, there are a lot of phenomena, very different phenomena, which are possibly related, in which we indeed see variations in the flux. And here are just a few pictures to show you things that you know already very well. These are examples of pulsars that show in the radio band nulling. They disappear for several periods. We have pulsars that in the radio band show a so-called modal behavior. They alternate between two or even more states in which their properties change. For instance, the average radio pulse profiles. We have pulsars that switch off for long periods of time, and during the switched off period, also their period derivative changes. There are pulsars that show a kind of bimodal behavior in the spin down, and again, this kind of variability in the radio properties correlates with the radio emission. These are curves in which you have in each plot something which is related to the shape of the pulse profile, and you see that it correlates with the variations in the spin down rate. So there is a lot of variety of variability in rotation power pulsars seen in the radio band. And a question that we are trying to ask is the following: are these changes something that is related to something in a sense minor that occurs just at the sites of particle acceleration? After all, in the radio band, we know that only a small fraction of the available spin-down power is emitted. Or are these changes related to something more global that involves the whole magnetosphere, as, for instance, the changes in spin-down seem to imply? And maybe now we are at the point in which X-ray observation can start to tell something relevant in this respect. So this basically was my introduction, and now in the following I will concentrate on these rotation power pulsars, which is the first or possibly one of the few X-ray valuable pulsars. First I will make a summary of previous results, and then I will concentrate on the results of the new campaign on this object that we had in 2014. So this is an ordinary pulsar. It has timing parameters that place it in the bulk of the normal pulsars. It is not a strange beast in some strange place of the PP dot diagram. Okay? It has a typical dipolar field of a few 10 to the 12 Gauss, and a characteristic age of 5 million years. What makes this object very interesting is that it is one of the so-called mode switching pulsars. It alternates between two states, a so-called bright and the so-called quiescent state. This is the paper reporting the Pushkino telescope radio observation in which this bimodal behavior was discovered. You see, these are the average pulse profiles. In the bright mode, it is brighter in radio. It is fainter in the so-called Q mode, and during the B mode, it shows a very regular pattern of drifting subpulses. Okay, and X-ray emission from this object was discovered by our chairman in 2003. It is a very rather faint X-ray source. With these data, there were basically too few photons to be able to detect pulsations, and even the spectrum was not constrained very much. It could be fit either with a black body or with a power law, and in both cases you see that the parameters were not very well constrained. The important advance came thanks to a coordinated campaign of observation in which XMM were used together with simultaneous radio observation by Wim Hermsen and collaborators, and this allowed them, first of all, to get more data in X-rays, but also to analyze the data separating the mode of the pulsar based on the radio data. And what was discovered was a very surprising result, that indeed the X-rays are variable, and they vary in anti-correlation with the radio emission. The fact that this is a rather faint source means that these results are best obtained if you use non-standard analysis technique, and in particular all the results that I'm going to present, and also the results that were presented in this paper, were done with the maximum likelihood analysis method. And you see here that the pulsations were detected when the source was in Q mode, while pulsations were not detected in the B mode, and you also see the difference in the X-ray flux between the Q and the B mode. Okay. Concerning the spectrum was rather well measured during the Q mode, which is the mode in which the pulsar is quiescent in radio but brighter in X-rays, and the spectrum was not surprising in a sense, the sum of the black body and the power. This is quite common in middle-aged pulsars. The spectrum in the fainter B mode was not so well constrained. It could be fit equally well by either a power law or a black body. The interesting result that was obtained was that going back to the Q mode data, if you divide the pulsed emission from the non-pulsed emission, I mean, if you extract the spectrum just during the pulsation, you can measure the pulsed spectrum, and the pulsed spectrum turned out to be compatible only with the black body. Okay, so to summarize these results, we have the total spectrum in Q mode, which is a black body plus a power law, the pulsed spectrum in Q mode, which is a black body, and if I take the power law fit to the B mode, fainter state, it was very interesting to see that the power law that fits the B mode and the black body that fits the pulsed flux in the Q mode are within the errors consistent with the two components that are used. This is dead. Can I have a better pointer? Can I have another pointer? Yes. With the two components that fit the total spectrum. Okay. So this led to the suggestion that, thank you, that what causes or what happens when the pulsar changes mode is that there is always some constant emission, which is a non-thermal emission, and when the pulsar gets brighter, this is due to the appearance of a pulsed thermal component, which is present only during the Q mode. Okay? And this, of course, is very interesting because it seems to require something quite drastic to happen in these objects. You have a new component that suddenly appears or disappears when the pulsar changes, switches between the two different radio states. And also it is puzzling because we know from radio observations that this object is a nearly aligned rotator, and we are looking at it from a direction which is not far from the rotational and magnetic axis. So we should be always seeing a hot polar cap. So we expect first that the pulse fraction be rather small if we are always seeing a polar cap. And it is also difficult to imagine that this hot spot in some way suddenly appears and disappears. Okay? So to try to better understand this object, we got more data. And we got a large program with XMM Neutron, and we had, of course, again, simultaneous observation. We had to use radio telescopes in Europe and in the States in order to have a continuous coverage of the X-ray data. This is one example of one session. We had 7 of these long observations. These are the radio data in which you see the different modes, QB, QB, and these are the light curves derived with the maximum likelihood analysis from the X-rays, in which you already can see that indeed the source changes its flux correlated to the radio modes. So which were the main results of this new campaign? First of all, from the timing point of view, now, thanks to the longer observation and much higher statistics, we were able to see that also in the fainter B mode, the pulsations in X-rays are present. and we could measure the pulse fraction as a function of energy. For the B mode, they are rather steady within large errors, while in the Q mode, the pulse fraction increases with energy. From the spectral point of view, for what concerns the Q mode, again, when the X-ray flux is higher, we basically confirmed the black body plus power law model that was already fit to the previous data. The same data can also be fit with a combination of two black bodies of different temperatures. For the B mode, and now thanks to the longer observation, we can see that the power law is ruled out, and a good spectrum can be obtained only with a black body. Of course, we can add also a power law to this black body. It is not strictly required from a statistical point of view, but both a single black body or a combination of black body and power law are consistent with the spectrum of the B mode. And then, as a next step, thanks to again to an extension of the maximum likelihood method, in which we used we called it a 3D maximum likelihood, in the sense that besides fitting the data in the spatial coordinates, we also introduced the phase dependence of the flux. Okay, so in this way we can simultaneously extract the spatial and temporal information, and if we can do this for different energy channels, we can extract simultaneously the pulsed and unpulsed spectra. And in this way, we found that the pulsed flux in Q mode is fit by a black body. This is the red spectrum here. The unpulsed flux is fitted with a power law. These are the residuals. If I try the opposite, so if I try to fit the pulsed spectrum with the power law and the unpulsed one with a black body, the residuals show us that this is not a good fit. For the B mode, again, we can fit the unpulsed flux with a power law and the pulsed with the black body. The residuals are very good. In this case, also the opposite fit would work. So we could also fit a thermal black body to the unpulsed and the non-thermal to the pulsed. The residuals are shown in this bottom panel. Okay. But since we see in Q mode a pulsed thermal component, we think that it is more reasonable to assume that also the correct description of the data in B mode is the same, rather than thinking that completely different components appear and disappear. So to summarize again, these are the two spectra, and what you see here is in black, you see the total spectrum in Q mode, which is a black body plus a power law in Q and B. And the red and the blue components show you the results of the phase, let's call it phase resolved analysis, in the pulsed and the unpulsed spectra, and their sum is consistent with the total spectrum in Q mode. So basically, the bottom line, the result is that the most plausible interpretation of this data is that both pulsed black body and non-pulsed power law are present in both modes, and both components vary when the pulsar changes the states. This is interesting to compare the properties of the thermal emission. You see that there are quite large errors in dimension of the hot spot and temperature, but it seems that a change in temperature at a fixed area is favored. In any case, the size of the emitting cups is rather small, smaller than the classical size that you would expect for a polar cap in a dipolar geometry. Another interesting result is this one. We try to look for some evidence of variation during the modes as a function of time, and this was motivated by the fact that indeed there are properties of the radio emissions that are seen to evolve during the B mode. Okay, and the only thing that we could find is that if we take the B mode data and we take just the initial parts of the B mode, so the first 3 hours of the B modes, and the last part of the B mode, means after 3 hours after the mode switch, it seems that the pulse fraction increases. This is results at the 2 sigma level, but is possibly interesting based on the fact that we know that something also happens at radio wavelengths. And this fact could also explain why the pulsation were not detected in the old data, because in the previous data, most of the time intervals in which the pulsar was in B mode were rather short. We did not have a good coverage of the latest part of the B mode. And this might explain why the pulsation in B mode were not detected. Another thing that we checked is to try to see the time scale on which the transition occur. And of course, with the statistics of X-rays, we cannot go to the single pulses as is done in radio, but by stacking all the transitions from Q to B, we have 15 of them, and 12 transitions from B to Q, we get these light curves in which it seems that we don't see any evidence of resolved variation in the flux. But the beam size is only 15 minutes in this kind of light curves. We cannot do better with the current instruments. I will skip this and go to the conclusions. So basically, the important point I want to make is that indeed the rotation power pulsars can show variability. We are just at the beginning of these kind of results. I think that this is a very promising new tool that can help us to maybe understand better also how the radio emission is produced in these objects. And we will hear more example of this in the next talk by Wim. Concerning 0943 in particular, the main conclusions of the new data is that both radio modes have basically the same kind of spectrum in X-rays, composed of a thermal and non-thermal component, and it seems that the pulsation are to be ascribed to the thermal X-rays, which is still something that needs to be explained, and both these components vary in a correlated way when the pulsar switches mode. Okay, this suggests that there is some kind of causal relation between the thermal and non-thermal X-rays, which is something not unexpected. You can imagine possibly that you accelerate particles in the magnetosphere to produce the non-thermal X-rays, but some particles are also accelerated backward on the polar caps and contribute to hit the polar caps and causes this relation. And the fact that the mode transition is not associated to a single component that appears or disappears maybe has some implication also for the kind of question that I was asking at the beginning. So is this something global or something local that happens in these mode switching pulsars? But this, again, is something that it is not easy to answer. I'm sure that there are different possibilities to explain this kind of results. I think that that's all I wanted to say. I thank you for your attention.
Thank you, Sandra. Questions, please. Oleg?
Sandra,
Yes.
Isn't it a little unnatural that the emission is brighter during the radio quiet mode if indeed there are some particles that appear, and they produce higher non-thermal X-ray and hit the surface? Shouldn't it be during the radio bright?
What you're saying is only partially correct. This terminology, bright and quiescent, is very misleading in a sense. I mean, it is something of historical. It is true that X-ray flux, the radio flux, is higher during the B mode, but what we see in the radio pulses is just it's not a complete view of what is really happening in the radio emission.
Okay.
Okay. So it is not really something related to the brightness or to the luminosity of the object.
Yeah, so then two follow-up sort of questions. So one is it possible maybe to model it with a different model, like an variable absorption feature, like broad absorption feature, instead of trying to component black body plus power law? And do you know on what time scale, when it switches from Q mode to B mode, the X-ray emission changes in flux? Is there a delay compared to switching in radio, or
we cannot tell? We cannot tell this. All we can say on the rapidity of the mode switch is that it occurs within 15 minutes. We cannot say more with the current data. And concerning the different kind of modeling, what we see is, I think, from the spectral point of view, more naturally explained in terms of different components than in terms of absorption. It is difficult to think two kind of absorption that works at all energies. I mean, we see that both the power law and the black body are changing in the two modes. No, it does not work. You need to change the flux in both components. Absorption feature. You must invent an absorption feature that keeps the same shape of the spectrum. Yeah, I mean you can, but it has to be a very broad feature, and then this introduces much more degrees of freedom. Remember, these are faint sources. I mean, this is the results of maximum likelihood spectral extraction. We cannot play too much with the models.
Okay, more questions, Igor.
Radio observations synchronous with your X-ray emission, or only X-ray, new X-ray observations, or with radio observations, new radio observations synchronous with this?
No, the radio observations used during the XMM observation were simultaneous with the XMM observation. When? This was November 2014 for the latest results, and it was in 2011, again October, November 2011, for the results published in Hermsen et al. 2013.
Other questions? Ali?
Thank you. Two questions. First, has there been a systematic search for X-ray variability in most of the variable radio pulsars?
Most of them, actually all of them, are fainter than this one.
Okay.
And the best candidates, of course, have been looked at after these results, and you will hear about that in the next talk.
And the other question is, what are the X-ray luminosities corresponding to these count rates?
A few 10 to the 29 ergs per
10
cent.
to the 29. Thank you.
So the efficiency is quite normal because the spin down power of these objects is 10 to the 32 2 ergs per second.
Any more questions, Matthew?
Matthew there.
Sandro, since you raised the possibility of return current heating of the polar cap, this is a very small polar cap size. So what constraints can you get from the pulse fraction on the polar cap size and the inclination angle?
This is another part of the puzzle because independent of the size of the polar cap, if you believe that the angles that are deduced for these objects from the modeling of the radio emission, it means that is a nearly aligned seen polon, it is difficult to explain such a large fraction with thermal emission unless you invoke some particular beaming or some different geometry for the magnetic field. To try to get a constraint, I think that any constraint you can get on the size of the emission regions is going to be very model dependent. Of course, if instead of the nebulae body you fit with an atmosphere model, you immediately get larger radii. Okay, but still quite smaller than the dipole polar cap. If you want to interpret this as evidence for multipoles near the polar caps, it's up to you.
Okay, thank you.
Any more questions? No more questions? Okay, then let's thank the speaker again. And the next speaker is Wim Hermsen, who will talk about, in a sense, about observations of a similar system.
Thank you very much. I'm continuing, let's say, the presentation on mode-changing radio pulsars, and I would like to present you results from 3 campaigns and make a comparison toward the end. I list here my collaborators, which are mostly radio people, and Lucien Kuiper from the in the X-ray analysis. So the introduction, more or less, has been given by Sandro in his talk, and he also present, let's say, the first result, the results on the 2 campaigns on PSR 0943, and I will need then also continue with similar campaigns on PSR 1822 and on BO 823. The last one are very preliminary first results, and in the end I will have a comparison of all 3. When I wrote the first proposal in 2006, in fact, it was still completely focusing on what's happening at the polar cap. I got then the idea that if the X-rays would also mode together with the radio, it might tell me something about whether we are dealing here with inner-accelerator caps, vacuum caps, or with space-charge limited flow models. But after writing the first proposal, it took me 4 years before we finally got the data. We had those beautiful papers by Michael Kramer showing that indeed there was mode switching as a global magnetospheric phenomenon. He was showing that the new dot is changing and that indeed plasma streams were changing, and it was global. There were 2 more papers later, 2012, seeing similar behavior for 2 more pulsars. And in 2010, when we got the first observations, Andrew Line had this very nice paper, and Sandro showed already the plots, where we could see that mode changing, pulse shape changing, was going together with new dot changes. At the same time, there was theoretical support that, let's say, the magnetosphere has global quasi-stable magnetospheric states. At the same time, there are papers that explain, let's say, the mode switching of the radio as a local phenomenon by discussing the inner acceleration gap, for instance, with partially screened cat models. And those models consider a critical temperature, and then it depends whether the temperature is just above the critical temperature or just below, whether you have a partially screening of the inner accelerator gap. So that was very exciting. And these are then the three pulsars I'm going to present results. The first pulsar, 0943, Sandro showed this very nicely. This is a nearly aligned pulsar. There we discovered, in fact, that the X-rays and radio change mode together. An old pulsar. And when you compare it with the other two, this one looks very much like PSRB 0823, which are about the same age. That the field at the surface is factor of 2 the same. The E dot, rotation energy loss, is close. That's different from PSRB 1822, which is very much younger and much more energetic, has a stronger magnetic field. This one is nearly aligned. This one we take as being orthogonal based on the fact that we see a pulse and likely an interpulse, but okay, there are other views on this in the radio community, also by Nikitina and Malov. 0823, that is also based on the radio parameters, an orthogonal pulsar. Just to show you the moding, types of moding, here you see for B0943 with LOFAR, it's in a bright mode, suddenly quiet and then bright. This is GMRT, you see again, here's the quiet mode, bright mode. The interesting thing is there is also a precursor in front of this main pulse, of this pulse, and that is correlating, in fact, in anti-correlation with the main pulse. So when the main pulse is bright, the precursor is on and is off and is on when the bright main pulse is quiet. This shows the moding. Okay, what is important to realize that the mode durations are typically hours here. For the second pulsar, the 182209, you see there's a main pulse and there's an interpulse, and that leads us to the assumption that this is an orthogonal rotator. We see both poles, and there's a precursor as well. We see the main pulse is moding from a bright mode to quiescent mode. The interesting thing is that here the interpulse is moding in anti-correlation. So when the main pulse is bright, it's off. When the main pulse is quiet, it's on. And that was already discussed in many papers. How do the two poles know of each other that they mode at the same time and then in anti-correlation? And there's no explanation yet. It's interesting to see there's also a precursor. And in this case, let's say the interpulse and the main pulse correlate in anti-correlation. The precursor in this case goes together with the bright mode. And here the mode durations are typically minutes. So the average will be about 4 or 5 minutes, then it's switching again. The last one, PSRB 1822. Here you see an example from LOFAR observations, Sobe et al., a recent paper. Here you see it's very bright. There's the main pulse. There's a much weaker interpulse. And here's a post-cursor. And you see here it was originally a nulling pulsar. They discovered here with LOFAR that in fact the nulling is not a null, but it's normally in a quiescent state, so a weak state. In fact, sometimes they still say it appears to be off, that is nulling. So there are different states. For us, let's say the Q state and off state we call Q state, and there's the bright state. Interesting, they're all different. Here the main pulse, interpulse, and post-cursor show correlated switches. They're all on or they're all off. Sander already presented the result for B0943. So the interesting thing there is indeed that we have in the Q mode, it's brighter than in the B mode. The thermal emission goes down by a factor of 3, the non-thermal emission by a factor of 2, but it's an anti-correlation. So when the radio is bright, the X-rays are weak. It has a very broad profile, and the pulse fraction in the Q mode is getting very high. And that is very difficult to explain. Sander mentioned, let's say, a possibility. 0943, you look continuously to the pole, and how can you get then a pulsation of up to 60%, because you should see something which is almost flat. And there, indeed, the magnetic field is sufficiently strong to have magnetic beaming. And indeed, that you have a pencil beam then and a broad fan-like beam. We have here some references. This could be an explanation. So then the campaign on 1822. We had 200 kiloseconds of excellent Newton observations, and of 2013 and March 2014. We had simultaneous observations with Westerbork, and it was also supported by Lovell and GMRT, because particularly in this case, when you mode every 5 minutes, you always have to know exactly in what radio mode it is. So you must really have always coverage. So if one of those radio telescopes would have RFI or wouldn't work for a moment, we could have the other. And indeed, we detected the source very neatly, but in fact we did see a double source. For the low energies, below 1.4 keV, the pulsar is dominating. Above 1.4 keV, there's a nearby source at 5 arc seconds. So you can only analyze this properly when you have used maximum likelihood, and that works nicely. We also discovered for this source pulsations, that is shown here. And let's say this is again a broad profile. You have here the main pulse, the precursor position, and the interpulse position. This is background subtracted. There's no background. These are all counts from the pulsar. As you see, it's broad, and the X-ray pulse is lacking by 0.1 in phase. The pulse fraction over this total X-ray range, 0.2 till, let's say, 2 keV, is 35%. So 35% is in this pulse, and the rest is below. And we don't see here, let's say, structure at the interpulse. But that is not strange, because you should realize if they both emit, and one is strong and one is weak, it sums up to this profile. So it doesn't tell us now that we don't have emission from the interpulse. When we determine the pulse fraction now as a function of energy, we see that it's getting very high, around 1 keV. And it shows, first of all, that the pulsed emission has a much harder spectrum than the unpulsed emission. But let's say for an orthogonal rotator, when both poles are seen, you should not have, when you have just isotropic thermal emission, such high pulse fractions. That's impossible. And let's say in that respect, I will come back to that later. We also think that here also somehow of magnetic beaming should play a role, or we should have other explanations. We looked for mode switching, and this is an example of our data, radio data. Here you see the pulse, main pulse, precursor, interpulse. Here you see the detection signal-to-noise ratio of the precursor, and you see really on, off. The main pulse is high when the precursor is on, as weak when the precursor is off, and the interpulse is doing this in anti-correlation. And in fact, we selected this on the precursor because there we have the cleanest separation of the two modes. We made many tests whether we see evidence for mode switching. I show you only this last one. We don't see evidence in this case for mode switching. And here we show, let's say, the pulse profiles in both modes, background subtracted, and the fact that they are on top of each other and they are drawn from the same parent distribution at the 97% level, we can say that the end pulse shape and flux of the pulse emission doesn't change, and flux of the unpulsed emission. We made additional checks, but we don't see any evidence for mode switching. Then the spectra. The total emission we can very nicely explain with two black bodies, and other fits with power laws do not give a proper description. And what we have there, we have two black bodies, a cool one with 0.08 keV or 0.96 million Kelvin with a large radius if you take a black body fit, and a hot one with a 100 meter radius, and this is 2.2 million Kelvin. And this is not strange because this is a pulsar 200,000 years old, a bit similar like the three Musketeers, Geminga, 0656 and 1052. They also have two black bodies. They have in addition a power law, but that is much weaker, and if you would scale it, it would be below our upper limits. In fact, when we now fit the pulsed emission and the unpulsed emission as well, we have proper fits with the same temperatures and similar radii. And let's say if I draw now a cartoon, the data is consistent with emission from both poles, and hot, let's say 2 hot pulses, 1 strong, 1 weak, and 2 cool pulses with different ratios, and they can give us then the total result. Let me say, then the point indeed is, how do we get indeed those differences of the two? And that again, if it's really an orthogonal rotator, it's difficult, or you really have to work with very different temperatures on either poles. Or again, you have to start thinking about magnetic beaming, where indeed the cooler component has a broader beam and can be seen from both poles almost at the same strength, a little bit stronger from the main poles, and you have then a narrower, hotter beam for the hotter component. So indeed, I said it already, you see then 2 components, one from the primary spot and one from the interpulse with the same radius, and then a cool component, you see indeed from both poles 30% more from the main pulse than the interpulse. Then I'd like to switch to the new campaign, and there we had 170,000 Newton seconds this year, so it's really fresh, end of April. And we had this together with GMRT, supported partly by LOFAR. And here you see indeed the mode switching I showed you earlier. And then the first observation in April, we indeed had a beautiful bright state in radio. Here you see 22 minutes in this case, but we have something like 7.5 hours of XMM observations in each observation. And beautiful profile. And during the whole observation, it was in B mode. Second observation as well, but the third observation, it was for 7-8 hours in the quiescent mode. Except of one occasion here, this is only 6 minutes, where there was bright emission, and the radio analysis showed that this was apparently a null state. There was bright emission, and then it was fading. This was only 6 minutes, and it was in radio less intense than during the bright mode, but it was clearly there. But for the rest, it was a completely quiescent observation. And the later observations, again, they were always in the radio bright mode. So we had 5 observations in radio bright mode and 1 in Q mode. In the first and the second observation, we nicely detected the source. This is a raw map. But on April the 24th, when it was in the quiet mode, we did not see the source, and the count rate was consistent with 0. The next day, or the second day after, in the radio bright mode, we do see again the X-rays. And it was also the 28th and the 30th. In fact, it was bingo. We see again simultaneous X-ray radio mode switching. So this is the second case that we discovered this. This was wonderful. But in this case, there are correlated switches. Radio bright with X-ray bright, radio quiet with X-ray quiet. So the opposite to what we see for 0943. In fact, I show here the count rates for the 6 observations. in 1 hour time intervals. And this is the average for all bright modes. And this is the average for the Q mode. And you see that already the X-rays can tell us in what state the radio is. That's pretty exciting. We see some hint of a decay, of these are a bit lower and this one is higher. This is all new for the last weeks. So we have to investigate the radio in more detail. But here the interesting thing is in the Q mode, the average is consistent with 0, but there's a hint that it's not always 0. When we now zoom in, you get this situation. This is the whole observation in Q mode. And here you have this bright mode, and we call this bright Q. And this is exactly this band. So the radio Q mode, it seems that we suddenly have a flux, higher flux here, and that it goes down. Triggered by these 6 minutes in radio in bright Q mode. In fact, when I select this bin, and this bin is 21 minutes, and I make a sky map, I have a 4.4 sigma detection, so we really detect the source, it's significant. Here it's getting weaker, but when I combine these 4 points, it's also more than 4 sigma. So even though the total observation gives 0, consistent with 0, we see indeed that something happened triggered by the radio upturn in the bright Q mode. And that's pretty exciting that you really see a very tight correlation. And we have now to analyze this in more detail. As I said earlier, the first quick analysis was this was a null and then bright and then it was fading over such a period. And this could be followed by the X-rays. And I remember you this figure because this figure was published. Here it was called B. It's clearly weaker in a radio than there. They said, hey, is it off here? And there's Q. And that's exactly what we think we have seen here. A null mode, something happens, also in X-rays, and it's fading. So we found this indeed pretty exciting. We also discovered for this pulsar now moding of pulsations in the bright mode. So this is the light curve. Here you have the main pulse, the post cursor and the interpulse. And now the X-ray is lagging by 0.2 in phase. Again, it's a broad profile. And from this is a very, I think exciting, that we have indeed now synchronous and correlated radio X-ray moding. In the bright radio mode, we have X-ray brightness with very strong pulsation. In a Q mode, we have no X-ray emission, at least with our statistics, except when we are in this bright Q mode. And the pulse fraction effect in the B mode is very high, almost 80%. This is a low value, but with very large error bars. And this for an orthogonal rotator, how do we get such enormous pulse fractions? Also there, you start to think about magnetic beaming, I must say. But okay, so this is again very odd. I said already these are first results. Up to now it's not ambiguous because these results are there. We started the spectral analysis. And there, let's say, the total emission cannot be fitted with single power or no single black body. Clear. And we have very nice spectral fits with 2 black bodies, again a cooler and a hotter one, with small radii. When we take this black body fit, indeed. So this is an explanation similar to 1822. But I must say, that's why I say it's preliminary, the total emission we can also fit with a 10% probability with a black body plus power law. With this temperature, 0.3 keV, small radius and an index of minus 2.5. However, in this case we get exactly the same values for the total and when we take just the pulsed emissions. In this case, when we fit the pulsed emission, it is not consistent. And this we have to study a little bit more in detail. As I could say now already, and it's particularly important for the interpretation, because you get a completely different discussion. These numbers are exactly the same as we found for 0943. So that would be exciting if that is the case, but it would also be exciting if that is the final fit. And the shape of the pulsed and unpulsed spectra are within statistics the same. It's clear with this large pulse fraction that the number of counts in the unpulsed emission is low. Again, here we can explain, let's say, this as a sum of two profiles, an interpulse and a main pulse. Of course, it's a bit shifted compared to the radio by 0.2. Let's say both pulses have a cool component and a hot component of 1.4 million Kelvin and 4.3 million Kelvin. In fact, this cartoon is not completely correct. This dip should be deeper in this case. Alternatively, lower probability, we have to see whether that is really consistent with all the data, that we have two pulses, both with a black body and a power law. And that would be similar to 0943, and okay, that we have to work out now further. But let's say now to compare the three pulsars, Moding pulsars. 0943, we have synchronous radio and X-ray correlations, but anti-correlated, and here the mode lengths are hours. 0823, again, synchronous radio X-ray correlations, but they are correlated. Also mode lengths of hours, on average a bit longer, but hours. 1822, no moding, short mode lengths of minutes, and we have been thinking maybe you need more time to get a stable situation, because if you mode every 4 or 5 minutes, maybe that's the reason why we don't see it. On the other hand, 0823, we see a reaction already when we have only 6 minutes of radio bright. But this we have to study now in more detail the radio, whether indeed when, in this case, the X-rays are fading, whether in the same way the radio are fading. All three pulsars have broad thermal sinusoidal X-ray pulses with high pulse fractions, and that's difficult to explain with nearly aligned and orthogonal geometries in both cases. It's just not thermal isotopic emission. X-ray emission from PSR 1822 can be explained as emission from opposite poles, each with cool and hot components. 0823 similarly. But as I said, we will look again somewhat detailed whether this would be equally likely, but this is giving at the moment a consistent result. And for 0843, indeed, we have there thermal and non-thermal emission. Well, then a question: how are the X-ray? Is the X-ray moding related to the radio moding? Is this global? Is this local? I'm not sure yet, because we really have to explain. It's one of the questions asked. Why are these different when the one is bright and the other is quiescent, and vice versa? Sandro is right that you might see only certain parts of the beam, but let's say when you have global changes, that might also cause changes of the profile. It cannot be absorption, because let's say this exact state is repeated every 5 minutes, 6 minutes, 7 minutes, or every 10 hours. So you always come back to exactly the same radio state as it was in the past. I have 2 more slides, if you allow me. I found this also very exciting and would just like to show you this. PSR 1822, our Westerbork observations, we have long observations because we need that for the X-rays. And these are the mode length intervals. And this is a continuous distribution. And this is from 10 seconds to 15 minutes. And you see that most modes have a duration of 4 or 5 minutes. And a short tail to, with a tail to 15 minutes. So that's very smooth. And this is summing up all modes. If I now make 2 distributions, one for the Q mode and one for the B mode, they are not the same at all. They add up to something very smooth, and these are completely different. And it looks like you have maxima and some valleys. And this is a whole discussion, but I will keep it short. Let's say PSRB 1822 can also has radio properties that you see a rotating carousel. You could make that interpretation just like 0943. In a bright mode, you have a very regular rotating carousel at the surface. And you have there the subpulse modulation P3. This has been also detected in a Q mode, a strong modulation, in this case long period, much longer than 0943. And that modulation is 46.55 times the period of the pulsar. In the B mode, there's a weak modulation. And these are apparently harmonically related, factor 2 till 3. And there, that modulation is 70 times P. And when you now look to the arrows, it looks like you see a maximum and a minimum at multiples of those modulations, which are different at the two poles. And these are indeed harmonically related. We can discuss this at length, but the idea is now that you have a duration, a period, which is really tied to the surface, a local phenomenon, and you have a period, you have mode durations, which is something global. So again, this somehow hints to a global effect. So I think the overall discussion, are we dealing here with local effects or global effects, radio, X-rays? I think this discussion open, it's pretty exciting. Thank you.
Thank you, Wim. Questions, please.
Ali.
Sergey.
Sorry if I missed it. Are angles between spin and magnetic axis independently known for these sources? And if yes, how precisely?
The spin axis, magnetic axis. Let's say 0823, I think that is a very clear case in the radio that it's orthogonal. 0943, I think everybody agrees that it's, I think, 9 and 15 degrees. So they really look to the... And 1822, we have in our paper, which appeared in January, an appendix where we discuss, let's say, all the radio data. And we agree with our Russian colleagues, Nikitina and Malov, that you cannot really conclude, but we finally conclude that given that we have there the main pulse and interpulse at 180 degrees, that is orthogonal. But there you might think that maybe it's at 16 degrees what they get. Even then, it's problematic to get these pulse fractions.
Thank you.
More questions?
Ali.
Sandra?
Can you tell something on the spectrum, or at least on the flux of the hard source near 1822?
Not at the top of my head. Let's say, it's dominating above 1.4 kV, and then, so the question, what is it? And it could be something that has to do with the pulse of the nebula. But that's something to look into. Yeah. And we, in fact, submitted once a proposal and didn't get time with Sandra. Because we wanted to... you don't have many counts. It's dominating above 1.4, so we have, something. Yeah. I don't know top of my head. Ali?
Ali, can you please give mic?
What are the X-ray luminosities of these three pulsars, and are they similar to each other and different regarding the X-ray output of other radio pulsars?
I think these are a bit similar. These are all till middle-age pulsars, and these are a bit similar, so 10 to the 29, 30. Let's say in this case, the few good candidates to do this work are these old pulsars, which are very weak X-ray sources. So that's why we sometimes see this source for the first time or detect the pulsations for the first time because of the long observations.
Okay, more questions? No more questions? Okay, then let's thank the speaker again. And actually all the speakers of the session, because it is the last talk, So the next step would be what? Taking photo, right? Yeah. Yeah, and I have a small announcement. There is a free banquet ticket, free dinner ticket. So if anybody wants it, please ask myself.